Welcome back. Now we will learn the basics of graph theory. This is the map of Königsberg, the capital city of East Prussia around 1905. We see 1, 2, 3, 4, 5, 6, and 7 bridges across 4 different land masses, including these 2 islands formed by the river Pregel. Königsberg, which became Kaliningrad of the Russian exclave territory, sandwiched between Poland and Lithuania after the World War II, is actually home to Immanuel Kant, the philosopher. Why do I talk about this? The graph theory, the mathematical tool behind network science, or combinatorics, if you will, is one of the few fields that can trace their origin to a single moment and place in history. It dates back to 1736 in Königsberg, which then was a thriving merchant city. They built 7 bridges across the river Pregel that surrounded the town. It is this peculiar arrangement that gave birth to a million-dollar puzzle. Can one walk across all the 7 bridges and never cross the same one twice? Despite many attempts, no one could find such path. The problem remained unsolved until 1736, when Leonhard Euler, a Swiss-born mathematician, offered a rigorous mathematical proof that such path does not exist. That is now considered the first theorem of graph theory, and deserves to be called a beginning of topology. Topology is the study of geometric properties and spatial relations unaffected by the continuous change of shape or size of figures. Within this framework, the 7-bridge problem could be reduced to this simple mathematical graph and generated many inspiring problems and solutions which network science is indebted to. It is a mathematical representation of a network. Graph is not exactly the same as network, but in most cases, the 2 terms are used interchangeably. So whether you are interested in the intranet composed of 4 computers, or 4 different proteins forming a dimer complex, or even for celebrities connected by the appearance in the same movies, you can draw this graph made of 4 nodes and 4 links for network analysis. By the way, down the road, I will call nodes and links interchangeably with vertices and edges. However, the reduction of the interacting real-world system to a mathematical graph is not necessarily trivial. In some cases, there's a unique, unambiguous graph representation as shown in this movie star network. We put an edge if 2 actors once have appeared in the same movie. But in general, the representation is by no means unique. Look at the case of protein-protein interactions. What do we mean by a link between 2 proteins? If a pair of proteins form a complex only in the presence of the 3rd one, shall we give an edge between this pair of protein nodes? Or if more than 2 proteins constitute a protein complex, should all the protein monomers be completely connected one another? It depends. It depends on the functional context of your problem. If you intend to discover a new drug target for, say, cancer treatment, or to find a hidden use of an old drug, which is so-called drug repositioning problem, you have to make every effort to make sense of clinical context. To continue the discussion on the proper representation of network system, we observe numerous cases where simple graph model with undirected binary links is too naive to capture the reality or to draw some meaningful conclusions. any serious geopolitical or economic analysis on the international trade should consider its directional nature. Depending on the purpose of your analysis, the balance between import and export may be more meaningful than their sum. Biochemical reactions are also often irreversible, and biological control logic is not reciprocal. So simple links between certain metabolites or gene products do not make much biological sense if we try to understand or hopefully engineer the metabolism of a living microbial cell. Likewise, every link is not the same in its influence. Think about the world's most crowded Gimpo-Jeju route to the once-in-a-week flown route between Christchurch, New Zealand, and Antarctica. Of course, the real world is the combination of all this. But don't take me wrong. I'm not saying we should go for the weighted digraph for more realistic model system. The power of abstraction comes at the cost of leaving out some irrelevant details. If Isaac Newton had known about the atomic structure of matter, would he have been able to discover the law of gravity? Maybe a bit far-fetched, but you know my point. Okay, without further ado, I will now talk about the characterization of a graph and more about numbers. Let's look at this sample network. What can you say if you have to say something about this network? First of all, it's sort of trivial, but the total number of nodes and links can be a meaningful piece of information. Here we have 8 nodes connected by 8 links. On average, each node has 2 links connected to its neighbors. Why 2? 8 divided by 8 is 1, but each link is counted twice when we count the number of neighbor nodes. This number of neighbor nodes, the node has, is called the degree centrality, or degree for short. So the degree is given to each node, and counting the degree is quite intuitive, almost no-brainer. But the non-trivial part of it is actually its distribution or statistics. Later, when we will study the empirical networks, including social, biological, or all the variety of technological networks, a big question is about the structure of a network. Because the structure of a self-organized system reflects the functional requirements and the physical constraints that have shaped the system, we are concerned about the statistics of all these degree centralities and other centralities too. With that regard, the degree distribution is a commonly used characteristic. Here, P sub k means the fraction of nodes that have degree k, or it can be interpreted as the probability that a randomly chosen node has degree k. So the sum of pk over k should be normalized to 1. In this sample network, this peripheral node 6, 4, 3, 8, 7 has degree 1. And the node number 5 has degree 2, and the node number 2 has degree 3, and the most connecting node, node 1, has degree 4. Right? If we plot the histogram, it will look like this. In comparison, if we consider a one-dimensional lattice, a set of beads threaded by a string, the degree distribution will be characterized by this single-peaked delta-like distribution. Once the degree distribution is given, we can formally compute the mean degree of the network, which is the first moment of the distribution. Likewise, we can obtain variance, which has to do with the second moment and other higher order moments to elucidate more detailed and the finer structure of the network. Okay, here are some real-world networks and their basic characteristics. Take these numbers for your information. For example, a movie star has 84 colleagues on average, and an average web page includes 4.6 links to other web pages, and each protein in a yeast cell has 2.9 binding partners, and so on. The mean degree is nothing but the first moment of the distribution. Though two distributions may share the same mean value, their higher moments may well differ. How do the degree distributions of real-world networks look like? This is the protein-protein interaction networks in yeast. The nodes are nicely clustered into subgroups with different color, representing the functional categories of the proteins, which requires another level of effort. We will learn more details about this network, but for now, its degree distribution is given like this. What do you see? The overall declining tendency tells us the higher the node degree, the less frequent we observe such nodes. Other than that, nothing much is to be seen from this plot drawn in linear scale. But if we redraw the same plot by using logarithmic scales on both horizontal and vertical axes, we will get this. The distribution now shows a feature that can be fitted by a linear function. Actually, this is a common practice in larger scale networks. What's the meaning of this linearity? We will come back to this point later, but the linear relation between log x and log y translates into a power law that x and y is correlated by a power function, like a y is proportional to x to the power of some number. Okay, now we discuss another way to represent a network without actually drawing nodes and links. For all the pairs of nodes I and j, if they are connected, then we give 1. Otherwise, we give 0. Thus, defined adjacency matrix for this sample network will look like this. For a simple graph where all the links are undirected or bidirectional, the adjacency matrix becomes symmetric. Because no self-interaction is present, the diagonal is also 0. Now let us focus on the node number 1 here. Since node 1 is connected to the neighboring nodes 2, 3, and 4, and 5, the non-zero elements of A sub ij should appear at the second, third, fourth, and fifth column of the first row. And their sum surely produces the degree of the node number 1. So this equality is obtained. Likewise, the total number of links can be computed by this formula. The factor of a half here reflects the double counting for the same edges. Actually, A sub ij is a network itself. A sub ij has full information about the network because it contains which is connected to which. For directed graphs, if we define the presence of a link from j to I as the condition for non-zero value aij, then the adjacency matrix is given by this form. Of course, you can change the order between I and j, so the value 1 is assigned to aij only if there is a link from I to j instead of j to I. Then the adjacency matrix will be transpose of this. But either way, A is not symmetric anymore. The row sum of aij over j gives the in degree of node I, because the destination I is fixed. Remember, the first index is the destination, and the second index refers to the initial node. So likewise, the column sum, the sum of a ji over j, now gives the out degree of node I. And now there's no reason for them to be identical, right? So the degrees and total numbers of edges are given like this. Then what about the adjacency matrix of a weighted network? Natural extension is that the aij elements should have continuous non-negative values. But why not negative values or even complex numbers? Think about it. Right, now I will define a couple of technical jargons that will be used throughout this lecture. Path is defined as an ordered set of nodes, N0, N1, N2, through NL. Okay? It is a trajectory that connects the initial node N0 to the destination NL. It may revisit certain nodes. So as long as the neighboring nodes are connected by a link, there's no restriction regarding the identity or repetition of identity of the nodes. One comment regarding the directed network is that a path should follow the designated direction, not the other way around. So the path 412 here, 412 is a legitimate path of length 2, but 214 is not. If we want to reach from node 2 to 4, then we should make a detour, meaning 2, 1, 3, 4 is a legitimate path. Distance dij is the least number of steps that connects the two nodes I and j. Here in this sample network, d42, meaning from the node 4 to node 2 has distance 2, but d24 actually is 3, because to reach 4 starting from 2, we need to go through 1 and 3. There's no direct path from 1 to 4. If a network is composed of disconnected clusters, a pair of nodes that belong to different clusters have infinite distance. Okay? In a directed graph, dij is not necessarily the same as dji. Sometimes when a part of the path is one way, dij can be infinite, even though dji is finite. Now, if you think about the possible number of paths that connect an arbitrary pair of nodes in 2 steps, that can be captured in the square of the adjacency matrix, because aij is non-zero only for the connected pair. The summand in here, aik times akj, is non-zero only if both ik and kj pairs are non-zero. Right? Now we extend this notion, the number of paths of length n between a node pair ij can be written like this. It's basically the ij element of the nth power of the adjacency matrix. Diameter d is often defined as the longest distance out of all the possible node pairs in a graph. And the average path length is defined as the algebraic mean of all the distances. But remember, this definition works only in a fully connected network. If you really want to consider a network composed of disconnected clusters, you may want to use an alternative measure, which is here the harmonic mean of the individual distances. Okay, if you think you succeeded in understanding all these quantities, you will have no difficulty in working out this exercise. I'll leave it up to you. A practical question for network analysis is to compute the distance between nodes, especially when the network is a large-scale graph. The breadth-first search is a conventional algorithm for this purpose. The original version was developed around 1945, so it's a classic algorithm. BFS travels over a graph from a root node and successively explores the neighboring nodes instead of visiting other nodes as far as possible, which is the case of a depth-first search. The breadth-first search uses a queue instead of a stack to remember and to get the next vertices to start a search. So it becomes easily memory intensive, but it is particularly useful in finding the shortest paths or finding all connected components and so on. Now, to compute the distance from a root node I, you first find its immediate neighbors and mark them as distance 1, putting those nodes in a queue. Then take each node out of the queue and find the unmarked neighbors to mark them as distance 2. Again, putting them in a queue. By iterating this process until there are no nodes left in the queue, we can label all the nodes in a graph with the distance from node I. If there are disconnected components, those nodes should be labeled infinity. Right. So far, our toy network has been a fully connected one, meaning any pair of nodes can be reached by any other node in the network. A common confusion is the distinction between a fully connected graph and a complete graph. A fully connected network is the one where any pair of nodes can be reached each other. However, the complete graph is the one where every node is connected to all the other n-1 nodes. Okay? Now, let's consider the following sample graph and ask ourselves what would happen if we removed this red edge. Okay? By cutting this link, the whole network is now disintegrated into two distinct subnetworks, yellow and green. In the adjacency matrix, this process leads to a block diagonal form, because now the node 1 and 4 loses connection to each other. The 1, 4 component and 4, 1 components of the adjacency matrix will turn to 0, which makes the block diagonal form of adjacency matrix explicit. And finally, the biggest chunk of the network, disintegrated subnetworks, is called the giant component. In a more rigorous usage, a giant component is a connected component of a given random graph that contains a finite fraction of nodes of the entire graph.